All right, chapter 10, aqueous solutions. We'll get through a little bit of this. We got time. So another part of dealing with aqueous solutions is not just whether things are soluble or insoluble and do we have a precipitation reaction and molecular and complete ionic and net ionic. There's also an extent to which it dissolves. So I prefaced this a little bit, sort of hinted at this in some of our previous lecture. Even things that we say are insoluble do dissolve to a certain extent, and things that are very soluble, well, there's a limit to how soluble they are, how much you can get to fit into a solution. If you've tried making really sweet lemonade or simple syrup, you've probably discovered this if you've tried doing it with cold water. It doesn't go in quite as well as in hot water. And that's the idea of solubility. So our solubility, this is usually something that you can look up. It's the amount, typically in grams, that dissolves in a certain amount of liquid, usually given as a volume, also sometimes given as a mass. For water, it's basically the same if we're talking about room temperature. For salt, the largest amount of salt that you can fit into 100 grams of water or 100 milliliters of water is 36 grams, which is a fair amount. If you have that limit of 36 grams of NaCl per 100 grams of water, we call that a saturated solution. A saturated solution means that no more can be dissolved. Sometimes we'll abbreviate saturated as SATed, and saturated sodium chloride, at least in the lab that I worked in, was pretty standard, and it would be SATed NaCl. And one of the ways that you could tell that you had a saturated solution of sodium chloride is you just dump a bunch of sodium chloride into whatever container you have, and as long as you have solid sodium chloride at the bottom, that means that no more is going to dissolve, and so it's saturated. So it's just ready to go whenever. And then if you need to make some more, you just add in a little bit of water, mix it up. Some of it will dissolve. As long as you still have sodium chloride at the bottom, it's saturated. So saturated means we're at our limit. If you played around with photo editing, a super saturated like color, you turn the color saturation way up, right? The colors get super bright and intense and unrealistic. It's a similar sort of thing with our solutions. We're maxing out the amount of, in this case, solid or compound that we can fit into the solution as opposed to colors in a photograph. On the other hand, an unsaturated solution just doesn't have that maximum amount. There's still room to dissolve. So we've just got less than that maximum amount. We can also have, on the other side, a supersaturated solution. And you might be thinking to yourself, well, that doesn't make any sense. If saturated is the most that you can have, how can you have a supersaturated solution? And typically, if you have a supersaturated solution, if you've got more than that saturation limit, then the solute will precipitate out. Another way that we would talk about this as chemists is it crashes out of solution. Crashing out usually means that that's not what we want to happen. And sometimes it happens in a spectacular fashion. Usually it doesn't. It's usually pretty boring. Our alum lab that we did, those crystals that we were making, we created a supersaturated solution of alum, and over time it comes out, it precipitates out as crystals. And depending on how much solution you have and how warm it is and how cool it gets and how much of your liquid you lose affects the rate that it comes back. We can also have supersaturated solutions. Since solutions are any two things mixed together, you can have a supersaturated solution like with a soda can. When you open a soda can, you're releasing the pressure and carbon dioxide bubbles start to come out of the solution. So that's another type of supersaturated solution. Supersaturated solutions are unstable. You can click on these links on your own time to look at sodium acetate solution. But this is one of the things that might show up in a supersaturated solution. So this is an ammonium nitrate crystal formation. So presumably this was a heated solution. The solution was allowed to cool, and that changed the solubility limit, became supersaturated, and so some of those ammonium and nitrate chemicals reformed as crystals that were really sharp and jagged. Solubility varies with temperature. Generally, for solids, like sugar, the solubility increases with increasing temperature. So sugar dissolves more easily in hot tea than in iced tea. If you're making simple syrup, you probably have a recipe for the amount of sugar that you add to the water, and you're going to heat up the water, add in a bunch of sugar, and then you can let it cool down. You don't make a supersaturated solution, and so it stays in solution. But it mixes in a lot easier than if you do it with room temperature or cold water. And this graph that we have, this chart over here, we've got temperature on the x-axis, so left to right, we're increasing the temperature up to the boiling point of water. And on the y-axis, we've got basically the solubility, how much we can fit in. So higher on that chart is more soluble. And for most of these, we can see an increasing trend. That means that as we're increasing temperature, solubility is also increasing. The way that it increases is not always linear. Some of them have a curve to them, but generally the solubility is increasing. Questions about anything so far? So a good thing to remember for this solubility of solids is adding sugar or salt to water. You can take advantage of the way that solubility varies with temperature to do recrystallization. That's what we did in the alum lab, or one of the things that we did in the alum lab. So you create a saturated solution at an elevated temperature. At an elevated temperature, we're going to have an increased solubility. And then, to get the recrystallization part to happen, you let the solution cool down. The solubility decreases, and that makes it a supersaturated solution. And over time, and given a nucleation site where it can start to form crystals, you'll start to form crystals. So solid crystals form, and when those solid crystals form, because we're assembling usually positive and negatively charged ions, it's just going to be the things that we want, the positive and negatively charged ions that form in to those crystals. So it tends to reject impurities, and this is one way of purifying chemicals. It's also a very finicky way of purifying chemicals, because sometimes if you just disturb the solution, for whatever reason, it's, all right, well, we're not forming crystals anymore. Okay, great. So this can be kind of annoying, but it's a convenient way to purify some solid substances if they're soluble in water. A fun way that you can utilize this at home safely is to make rock candy. So if you've ever been to a store and they sell rock candy on like a little stick or whatever, you can make it at home. So the way that you would do that is you make a saturated sucrose solution, so just table sugar in water, heat it up, dump as much sugar as you want into it, the more the better, and then dangle a string in that solution. So you can get a mason jar, or you can get a Yeti that you're not using, or some other insulated thermal flask. Dangle a string or put a little stick in it or something, and leave that to cool for a couple of days. As that cools down, you'll be forming these sugar crystals. Those will typically form on the string, and you can do this as many times as you want. So you can pull it out, make another supersaturated solution, dip your rock candy back into it, and keep growing your crystals as big as you want. You might also be able to color them with like some food dye, but that's up to you. If you long for red 40, get after it.
I'm a blue 5 kind of guy.
Hey, you can blue 5 as well. You can, whatever the yellow color is. I don't know all my numbers. So that's an example of using recrystallization, using solids and solubility to your advantage to make fun rock candy. So that was looking at solids in water. Gases also form solutions in water. And our example for that is a can of soda. So in a can of soda, typically they're pressurized, my understanding, to 2 atmospheres of carbon dioxide in the can of soda. So that when you crack it open, whatever elevation you're at, you've got plenty of pressure keeping that carbonation in your soda. If you leave your soda out for long enough, what happens?
It loses pressure?
It goes flat, right? It loses that carbon dioxide. It doesn't have a very good solubility limit, and so over time that'll just leave. There's not enough carbon dioxide for it to stay in the solution. That's why they ship pressurized. If you pressurize it, that forces more of the carbon dioxide in. We'll get to that. Most liquids, basically all liquids, exposed to air contain some dissolved gases. They'll just dissolve out of the air. And this is a good thing. Lake water and seawater both contain dissolved oxygen that fish need to breathe. If you don't have oxygen getting back into the water, then the fish don't breathe. And when fish don't breathe, they die. And our blood also contains dissolved gases, which is also good. Our tap water, especially if you have well water, sometimes that'll contain a lot of dissolved gases, and you might need to shake it up to get rid of those dissolved gases. The solubility of gases in liquid decreases with increasing temperature. So we've got a similar graph here. On our x-axis, we've got temperature in degrees Celsius, so left to right we're increasing temperature, and on the y-axis we've got solubility. So higher up means more soluble. At low temperature, close to freezing, you can see we're helium, nitrogen, carbon monoxide, oxygen, methane. Right, we have higher than when we are at high temperature. So as we heat up our liquid, our solubility drops. One application of this, if you like really, really fizzy drinks, really fizzy soda, warm soda is actually going to fizz more than cold soda because you've got a lower solubility. It also means that warm soda will go flat faster. So this would also be something that you could try safely at home as long as you have 2 cans of the same drink. Put one of them in the fridge, leave one of them out. You could also just like feel them. Like if it's a really, really cold can of soda, it kind of flexes a little bit. If it's a warm can of soda, it doesn't do that. You could also just do that without having to, waste a can of soda. That's kind of all I have to say about that. One way that I like to remember the solubility, since it's normal for people to understand that solids dissolve better in hot liquids than in cold liquids. The gas one kind of people don't get. That one seems to kind of confuse students a lot of the time. If we look at energy or temperature, what's our lowest energy state of matter? Solids. Solids have the least energy. What has more energy than a solid? Liquid. And what has more energy than a liquid? A gas. So when we increase the energy, or the temperature, what happens to solids? Do they become more or less like a liquid? They become more like a liquid. Heating makes solids more liquid-like. And because they're more like a liquid, they dissolve easier. What happens if you increase the temperature of a gas? Does it become more or less like a liquid? It becomes less like a liquid, so as you heat it up, it becomes less like a liquid, and so it decreases in solubility. The other way I could have wrote that is to make gas more like a liquid, you have to decrease the temperature, decrease the amount of energy it has, then it becomes more like a liquid and it's going to increase the solubility. Any questions about that? That's the way that I like to think about it. I think that's a cool way to think about it. If you just want to memorize it, that's fine too. But you should know how solubility generally tends to work for gases and solids in liquids. The thing with the cans of soda and increasing the pressure causing more to go into the solution, that's this slide. So the solubility of gases also depends on pressure. Henry's law states the higher the pressure of a gas above a liquid, the more soluble the liquid is in, or the gas is in the liquid. One way we could think of this is higher pressure in the air. If there's a bunch of pressure in the air, some of that is going to go into the water. It's forced into the water by that pressure. It might not stay there for very long, but it's going to go in, it's going to dissolve in the liquid. If you increase the pressure in the air, more of it is going to escape into the water. It's going to dissolve into the water. So higher pressure forces more gas into solution, aka it dissolves. That's kind of the big takeaway for Henry's law. A can of soda is typically going to be pressurized with carbon dioxide. And when you open that can, the pressure is released. It drops to about 1 atmosphere, because that's the atmospheric pressure. And that causes the solubility of carbon dioxide to drop. One of the reasons that you would want to refrigerate your bubbly beverages, like champagne or sparkling wine, things that you can't reclose, if you refrigerate it, it stays colder, you're going to have a slightly higher solubility limit for your gas, your bubbly, so it's going to stay bubbly longer. It still might go flat eventually, but it's going to last longer than if you leave it out on the countertop. It's also just nicer to drink cold. And that applies for like 2 liters of soda as well. They'll go flat eventually, especially if you keep opening them and closing them because you're releasing that pressure. That's another way though that you can preserve your CO2. Keep it bubbly. One of the ways that we can specify solution concentration is with mass percent. Our mass percent is grams, because it's mass, per 100 grams of solution. A solution with a concentration of 14% by mass contains 14 grams of solute per 100 grams of solution. In sugar water, what is our solute? It's the sugar. Just to review what a solute is. It's the minority component, or the other way that we think of it is it's the thing that's not the water, since the water would be the what? Not the solution, be the solvent. The solute and the solvent together is the solution. Our formula for mass percent, mass of the solute over mass of the solution, which is the solute plus the solvent. And then we multiply it by 100% because it's a percent. And the denominator is the mass of solution, not the mass of solvent. Pointing that out because we'll have an equation where we have mass of solvent in the denominator instead of mass of solution. Questions about this? All right, an example. Calculate the mass percent of a salt solution. Mass percent of a salt solution containing this many grams of sodium chloride and this many milliliters of water. We're going to assume, like we usually do, like it's usually safe to do, that the density of water is 1 gram per milliliter. That means you can just switch grams and milliliters. They're interchangeable. Our formula is mass percent equals mass solute over mass solution times 100%. Between sodium and chloride and water, which is our solute?
Sodium chloride?
Yeah, the sodium chloride, the salt, is going to be our solute. It's both the minority component and the solid. So in our equation, we're going to put 12.8 grams sodium chloride. What goes in for mass of solution? What's included in the solution? There's two things.
Solute and solvent.
The solute, the minority component, and the solvent. In this case, we just have 2 ingredients. You could have more than 2 ingredients. So that's going to be our 12.8 grams of sodium chloride and also 357.1 grams of water. You could have also added those up beforehand, and that would be your mass of the solution. It is milliliters of water, and milliliters are grams for water. Since the density is 1 gram per milliliter, we can just flip-flop grams and milliliters as much as we want for free with no brain power required. So this milliliters can become grams. And times 100%. Questions about any of that setup? An important thing to remember when you're putting this into your calculator, if you do it this way, you're probably going to want to put parentheses around your denominator, otherwise you'll get the wrong answer. Looks about right. Okay, so our mass percent, this is 3.46% sodium chloride. If you got like, let's see what it would be. If you got 35,711%, you forgot to use Prince.